Hello friends, welcome to Mu Lessons. In the previous video, we have seen how the diodes are made. We have seen the working principle of the PN junction diode, P-type, N-type diodes, several types of biasing like the forward biasing, reverse biasing, and some of its characteristics and some of its regions like active region, cutoff region, saturation region, and their working. So on the basis of the biasing, today we will start with the second part of the PN junction diode, that is the application of the diode. So in our daily life we are using these several applications of diode, like they can be used as rectifier, Zener diodes, LEDs, photodiodes, solar cells, and basically these are made on the basis of how they are biased, on the basis of the biasing. So this is a quadrant picture. You can see the rectified diode operates in the quadrant 1 and 3. In this part, the pink region, the light emitting diode and laser diode operate in quadrant. You can see in the second part, in the first quadrant they operate. Zener diode and photodiode operate in the quadrant that is shown in this diagram. That means there are several operations on the basis of which they have been biased. So let me revise. This is the first thing. You have seen that you have read the diode characteristics in the first video. So basically the rectifying diode operates in these forward characteristics and with this reverse characteristics in the first and third quadrant. The LEDs, they always work with the forward characteristics, that is in the active region is the first quadrant. The Zener diodes and the photodiodes, they work in the reverse condition, so they act in this quadrant, that is the third quadrant. And finally the solar cell acts in the fourth quadrant. So on the basis of their operation, we have separated all these three on the in these quadrants, so that will be easy for you to remember. Now starting with the first application, that is the rectifying diode. You have read already there are two types of rectifier, half wave and full wave. In case of half wave rectifier, for a total signal only half of its signal is extracted and other is made zero. But in case of full wave, the whole signal is made positive, that is there is no polarity change. The fundamental application of this rectifier diode is to make use of this non-linear current IV characteristics, utilizing it in the rectifier circuit. So these rectifier diodes are used to convert the AC voltages into DC voltages. In case of AC, we have the magnitude along with the change in the polarity, but after rectifying them we will have the same magnitude but the polarity will not be changed. So during the positive cycle of the AC, Vin is given as, you can see the cursor, Vin is given as Vm sin omega t, or in this case we have used the term Vp, that is a peak value of voltage sin omega t, and the output voltage V output is equals to Vp sin omega t minus 0.7, that is the drop across the diode. And during the negative cycle, the output voltage is 0 because it is a half wave rectifier. Now you can see the circuit diagram of half wave rectifier. An alternating voltage of Vin, that is Vp sin omega t, is provided, is applied in series with the diode and a load resistance across which the output is to be measured. So now see, let us imagine there is a AC source. In the positive half cycle, it will conduct, this diode will conduct, and the output will be shown as the positive side, that is Vp minus Vb. That means total peak voltage minus the drop across the diode. But what will happen in case of the negative cycle? When a negative potential will be given through this diode, it will act as a reverse bias condition and no current will flow through this diode. That means you can imagine this circuit as an open circuit in the negative cycle. So there will be no current flowing through this, and hence the amount of current is 0. And again the same cycle repeats, we get same positive cycle, and for the negative cycle 0. So this is the basis working principle of half wave rectifier. Now we have the average value for half wave rectifier as 1 by t, 0 to t by 2, Vp minus 0.7 sin omega t, and by solving mathematically you get this result, which is approximately equal to 1 by third, that is 1/3 of the peak voltage. Now since half of the input cycle the diode is in reverse bias mode, therefore it is necessary to know that the peak inverse voltage. This is one more important term regarding the rating of the diodes, that is a peak inverse voltage. What is the maximum reverse voltage it can accommodate, that is given by this PIV. If the peak voltage Vp of the circuit is larger than the peak inverse voltage, again I repeat, if the peak voltage Vp is larger than the peak inverse voltage, the diode will eventually be damaged by high voltage. So the applied voltage should be less than the peak inverse voltage of the diode to make it work properly. And that is the reliable condition for a half wave rectifier to act. So this is the condition, Vp should be less than equals to PIV. Now suppose if a capacitance of capacitor C is connected in parallel with the resistance R, and this capacitor would behave as a filter to the circuit. So what will be the output? In this case there will be some clipping on the top of the top of the signal. You can see the resultant output. The same half wave rectifier we will get, but there will be some clipping due to clipping, or you can say the ripples have been removed. That will be produce a VPP ripple voltage riding on the DC voltage. So this is the characteristics of adding a capacitor across it. For a small ripple voltage of VPP, you can see here, as compared to the DC voltage level VDC, this condition is called light loading. And the change of ripple voltage delta VPP follows this equation, that is current into time per capacity C, and that can be often written as like this. Time can be written as 1 by frequency, and hence you will get this result also. Now in that case the DC voltage VDC is equals to Vp, that is the peak voltage, minus the drop across the resistor, that is 0.7, minus Vpp by 2, that is the drop across the capacitor. So the net DC voltage will be Vp minus 0.7 minus Vpp by 2. Now further substituting in the above equation which you have got, we will get the VDC as in this form. So it depends upon what components are combined with the circuit, and after that we can easily identify how it can behave. This is also the similar diagram of the rectifier, but in this case it has been a full wave rectification circuit. So in this circuit we are using a transformer n:1 ratio, that is the center tap. You can see here CT, center tap transformer, and we are using two diodes D1 and D2 respectively. So what happens in this case, whenever the positive signal goes through D1, you have to observe it very keenly. Whenever the positive signal goes through this D1, we will get an output, and that magnitude is given by the first cycle. And whenever the negative cycle will go, D1 will block the negative cycle and D2 will allow to pass the negative cycle. So for D2 again rectification will take place and we will get the second cycle. And this is the average value, that is the VDC, and as capacitor is attached to it we will get some ripples, that is VPP, and will continue so on. But this is the main basic thing about full wave rectification, how it works using the two diodes D1 and D2. This is a type of center tap rectification, center tap full wave rectification. Now there is one more full wave rectification technique, that is a full wave bridge rectifier. In this case similar thing happens. Let us concentrate on the first part. that is the blue box part which I have made. Let us first concentrate in this. So here we are using a transformer, and in this case we are using a full wave rectifier, D1, D2, D3 and D4 in cyclic order. Now for the first cycle to come, positive cycle, it will pass through D4 and D2. So for the first cycle, D4 and D2 will be active, and for the second cycle, D1 and D3 will be active. So this arrangement of diodes is a bridge, behaves as a full wave rectifier bridge. Once again I repeat, during the positive cycle of the signal, the maximum voltage at node B is Vp by N, because the net peak is V and there is a ratio N is to 1, and the minimum voltage at node A will be 0 as it is connected to the ground. Therefore the reverse bias voltage D1 is Vp by N, and this diode in this case is reverse bias. Thus the peak inverse voltage is given as Vp by N. So the net peak inverse voltage rating of this diodes is Vp by N. So this has made you quite clear about the working of bridge circuit, that is the full wave bridge circuit. Now coming to the second application, that is a Zener diode. You have listened about this Zener diode. They are always utilized in the breakdown region. In the quadrant picture I have shown you how it works on the third quadrant, that is a reverse condition or the breakdown voltage, you can say. At the breakdown voltage, the reverse current increases rapidly with a small increase in the reverse voltage, and this makes it useful as a reverse bias or a voltage regulator. It operates in the third quadrant of the IV characteristics, and we will see it later. So in this case we have connected V in input source, and this Zener diode, you can see the sign of this Zener diode. This Zener diode is connected in parallel to the source. So once Va is greater than Vz, the voltage at node shall be maintained at the reverse bias voltage, that is Vz. Now applying Kirchhoff's law, we can easily find this Is is equals to IL plus Iz. In this node A, Is is equals to IL plus Iz, and applying Kirchhoff's voltage law, you are well acquainted with this current law and voltage law as you have seen the videos of DC circuit. It is given as minus V in plus ISRS and plus Vz equals to 0 for the first loop, and we get Rs equals to V in minus Vz by Iz plus IL. So Iz is the Zener current flows in the Zener diode in the breakdown region, and IL is the load current in the circuit. We have seen the V in is the supply. So this Zener diode also has a maximum power rating, that is defined as a maximum allowable current flows into the diode multiplied by Vz. So that is the maximum power of the diode, Zener voltage into Zener current flowing through the diode. So the basic for the fundamental thing you should remember, Vz always acts in the reverse bias condition, or you can say the third quadrant, and its power rating is given as Zener voltage into Zener current. Now the third type, that is the light emitting diode, we used in our houses. It produces light because the principle of recombination of the majority carrier in PN junction produces the light, and it is also known as injection electroluminescence. It is better to remember this word. It is basically converting the current into light, as the term says, light emitting diode. When we apply a current across the diode, that current is utilized by it and it converts into light. So it acts in the first quadrant. I have said it before from the picture IV graph. Forward biasing of the PN junction injects the majority carrier across the junction, Thereby it will recombine with the majority carrier on the other side of the junction to produce a visible light, and that is what we call the light emitting diode. You can go through this light emitting diode theories from your book. This is similar to that of the working principle of diode, but this particular diode always work in the forward bias condition, so that the majority carriers will be emitted and we will get the light. The working principle is similar to the LED and is essentially the forward bias PN junction in which the recombining carrier produces light. So I think this picture has given you a nice view about how it acts in the active region. The light is emitted in the active region. Now coming to the next thing, that is the solar cell. This is just the reverse of LEDs. This solar cell converts the optical signals into current. In case of LED, we are supplying current and we are getting light, but in this case we will supply light and we will get the desired current. That means it works in the fourth quadrant, just the opposite of the first quadrant. These are known as photodetectors, or better known as photodiodes, which operates in the third quadrant, and solar cell is using in the fourth quadrant of the current voltage IV characteristics. In this case, what happens? The magnetic area is generated across the depletion region by differing the provided with the diffusion length of depletion region. Depending upon the amount of illumination received by the PN junction, the reverse saturation current is set and it increases substantially. And this method of creating magnetic carriers is known as optical injection, or in this case you can say the carriers are called excess carriers because they are extra to those generated thermally. And this is the typical structure of a photodetector. All these applications are just on the basis of how they are biased and the region characteristics in which they are working. This is a very famous diagram. It is a solar cell, for you will read in higher studies. Very efficient cell, solar cell. When incident photons are placed in this cell, there is a movement of the magnetic charge carriers, and due to that extra magnetic charge carriers, thermally induced EMF is produced, and that results in the flow of current. The power is generated from the solar cell because it operates in the fourth quadrant of the current voltage IV characteristics. The negative generated current, which comes from the magnetic carriers and the forward bias of PN junction, gives rise to the negative power, which will mean that power is generated. This is the VI characteristics of solar cell. It works in the fourth quadrant. So these are very small things to remember regarding the application of diodes. You can also calculate the efficiency of these solar cells, like efficiency is power maximum output by minimum power input. So in this case, efficiency is given as P max by ISC VOC. From the diagram you can get the P max equals to I max into V max, that is output, and for input power, that is the short circuit current and the open circuit voltage, and this gives the efficiency. We can also write the power input as P solar, where P solar is the amount of solar power reaching the cell, that is, you can say the input power reaching the cell. Ideally, this efficiency would be equal to 1, indicating that all incident radiations has been converted to electrical power, but solar efficiency is less than 30%, and utilizing this gallium arsenides. So these were a lot regarding the application, and now there are some more applications like the clipper and clamper circuits. These clipper circuits are also called the limiter circuits because they are used to cut off the unwanted voltage, and there are 4 types of clipper we can have, that is the negative series clipper, positive series clipper, negative shunt clipper and positive shunt clipper. As the name suggests, you can easily identify which are negative series clipper. So the negative series clipper clips the negative portion of the AC voltage, while the positive series clipper clips the positive portion of the AC voltage. You can see from this 4 diagrams the 4 types of clipper configurations. So starting with the first one, you can see in the first part the positive part is allowed to move and the negative part is not allowed, so it is a negative clipper. In this case the diode is reverse bias, so positive part is not allowed to move and the negative part is allowed, so it is a positive series clipper. And similarly, when these diodes are used in shunt, this acts as a negative shunt clipper, that means it passes the positive part, and this diode, when made in parallel to the AC source, acts as a positive shunt clipper. So on the basis of the design or configuration, you can say this type of clippers acts in the four modes. So there are several calculations regarding the Kirchhoff's voltage law. Using this Kirchhoff's voltage law, how the clipping takes place. Now this picture shows you the operation of the negative shunt clipper. When the AC source is given across this diode D1, the current flows and we get the output. When the positive part encounters this node, this diode is in the reverse bias condition, so no current flows to this diode and we get the net output as positive. And when the negative part goes through this diode conducts and no current is flowing across RL. So for this we get the resultant as V in, that is V in into RL by RL plus RS. You have to analyze these types of circuits. There is no mugging of way out for this. Similarly, this acts as a positive half cycle operation, and this is the negative half cycle operation of a negative shunt clipper. And in case of a negative shunt clipper, negative side, what happens? This source is reverse, that means the negative side is on the top and the positive side on the bottom. So in this case the current flows in the opposite direction and we get the net voltage across RL is equals to the voltage across diode D1, that is minus of 0.7 volt. So for a negative cycle we have this diagram. Similarly, we can have some more examples of clippers, positive clippers and negative clippers. Now coming to the last part, that is the clamper. A clamper is a circuit designed to shift AC from either above or below a reference voltage. In this case, these AC sources are either moved below the reference line or moved above the reference line using the same diodes. It can be negative clipper diode or positive clipper diode depending upon the configuration. So seeing this picture, during the positive cycle of the AC signal, the diode is in forward biased mode and the capacitor will get charged. So its amplitude Vp due short time is constant. And during the negative cycle of this AC, the diode is in reverse bias condition and likely to discharge through this capacitor, and it will maintain its charge. Thus from the Kirchhoff's voltage, if you apply this Kirchhoff's voltage law, in this case the maximum voltage across this load RL shall be approximately equals to minus 2 Vp if the input voltage is V in equals to Vp sin omega t. So by solving these things we can get how this clipper and clamper circuit works. You just need to analyze them. You have to practice more because there are no such mugging way for these clipper and clamper circuits. We have to analyze the circuits. Thank you.